Greetings, calculus students. Mr. Allen here. Today we're going to look at applications of derivatives or differentiation. Again, if you were interested in getting this PowerPoint, it is on the Canvas webpage, so please feel free to get that. Let's go ahead and get started. First things first, critical number. A critical number, by definition, is when f prime of c is equal to 0, or where the function is not differentiable. So for example, at this point right here, and this would be looks like the x value of about -3, the derivative there is equal to 0. The slope of the tangent line is 0, so that means that x equals -3. -3 is a critical number. Similarly, right here, f prime of, let's see here, 1, 2, 3, 4, 5, f prime of 5 is equal to d and e because it's a sharp turn. So therefore, 5 is a critical number. So there's two possible situations for critical numbers. Most common is when the derivative is equal to 0, but the other one is when the derivative is equal to d and e. The reason that they're important is theorem. If f has a relative min or relative max at x equals c, then c is a critical number. Now this is an if-then statement. So if it is a relative min or a max, then it was a critical number. Backwards does not work. So just because something's a critical number does not necessarily mean it's a relative min or max. So be careful about that. Okay, the next concept is increasing and decreasing functions. By definition, if f prime of x is greater than 0 for some points on an interval, then we call it increasing. If f prime of x is less than 0 on some interval, then it is decreasing. So for example, here, if you draw a tangent line, you can see that the slope of that tangent line is positive. That means f prime of x is greater than 0, therefore it's increasing there. Similarly, if we look right here, this tangent line, its slope is negative, therefore it is decreasing. So increasing and decreasing is defined by the sign of the derivative, first derivative. Extrema on an interval. We have relative extrema that are called mins, and we have relative extrema that are called maxes. Now this right here is obviously a min, and in this case it's actually what we call a global min, or a global min, or the minimum period. This is basically where the function, the value of the function, that's what f of c means, is less than or equal to all of the other values of the function. And a max, for example, let's look at this local max. Now, local max just means in this kind of vicinity here, this particular value of the function is greater than all of the other values. So that's what we mean by a maximum or a minimum. To locate extrema, there are some steps that you should follow. Number 1, find critical numbers. I've already talked about those. Number 2, go ahead and evaluate the value of the function at those critical numbers. Number 3, don't forget to check the endpoints. This is if you're on a closed interval. If you're on a closed interval, you need to make sure you check the endpoints. And then finally, number 4, the least of these values is a minimum, and the greatest is the maximum. Again, this is on a closed interval. This is not local extrema. This is extrema, period. Concavity. We say the function is concave up in this area here. It is concave up when f double prime is greater than 0. The second derivative of the function is greater than 0. This is concave up. Here we have concave down. This is where the second derivative of the function is less than 0. That's concave up, concave down. What are what we call those points right here where it switches from concave up to concave down? I'll give you a hint. Okay, there are two very important tests for determining local extrema, and those two tests are the first and second derivative tests. The first derivative test is called the first derivative test because you use the first derivative of the function to determine the relative min or max. And what you want to do is you want to look for a change in sign. So for example, if f prime changes sign from positive to negative, we know that that's going to be a relative maximum. The second derivative test uses the second derivative of the function. And so what you basically do is, let's say you find that the critical number is 2, critical number equals 2, and then you find that f double prime of 2 is, let's say, negative 3, then what do we have there? Well, that's going to be a relative max. Okay, that is a relative max if the second derivative of that particular critical number is negative. And the reason is because if the second derivative is negative there, that means it's concave down. So that makes it a max. Now, guys, I'm not going through and doing examples, concrete examples of each of these. I'm just kind of reviewing the big ideas. Okay, mean value theorem. This is something that a lot of students kind of struggle with. Here's what it means, no pun intended. Let me get a green color here. So this red curve, that is our function, okay? And this blue line right here, this blue line, this is the secant line. That is the average rate of change. And let's say that the average rate of change here is, I'm going to just write m equals, let's just say 1 to keep, actually, let's make it 1/2. Let's say the average rate of change from point A to point B is 1/2. That's just the slope formula, okay, which is this right here. The mean value theorem says that if the function, that's this red guy, if this function right here, if the average rate of change of that function on the interval from A to B is 1/2, then guess what it guarantees us? It guarantees us, as long as this function is continuous and differentiable, that there has to be some point called C between A and B where the tangent line has that same slope of 1/2. This is called the mean value theorem of calculus. It's actually very important. Okay, I think this is the last example here. Yep, good. So we're almost done. We got a few more minutes left before my 10-minute time limit. I'm going to try to complete as much of this as possible. So the last piece of this applications of differentiation in the unit that we're supposed to review is optimization. Now, these are basically story problems. So here I have this curve, y equals 1 over 1 plus x squared. This is this red curve. I use Desmos to graph it. And it says we have a rectangle that is going to be, one side of it is on the x-axis. So I'll just draw like one rectangle here. And then it's going to go up, and then it says 2 of the vertices, so that one there and that one there, are actually on that curve. And it says, find the coordinates of the vertices of the rectangle with the maximum area. So what we're trying to do is we're trying to maximize the area function. So we got to write the area function. Well, area is equal to length times width. Okay, so, or if you want to call it, we could call it length times height. How about we do that? Length times height. So it's got a length and it's got a height. Okay. So the length here, I'm going to claim that it's x plus x. And the reason I'm doing that is because if you pick any value x, let's say 2, okay? If x is 2, what's this total length going to be? Well, it's not just 2, it's also this 2 over here, so 2 plus 2, so that's going to be x plus x. And then what's the height going to be? Well, the height's going to be the y value. Now we can simplify this to 2x times y, which can be further simplified because guess what we know about y? Y is equal to 1 over x squared. So this is the same thing as 2x over 1 plus x squared. This is our area function, and this is written in terms of x. This is the key to this problem, and this the hardest part of the problem probably is setting that up. So if we want to maximize that function, the first thing we're going to have to do is we're going to have to find the critical numbers. So we're going to have to do the derivative of A. And I'm going to cheat here a little bit. I've already done this before we did the video, but you would have to do the quotient rule. And you get an answer of -2 times x squared minus 1 over x squared plus 1 squared. So that's by the quotient rule. Now, critical numbers are any numbers that can make this equal to 0 or d and e. Well, nothing can make the denominator 0, so that's just nothing. Okay? What can make the numerator something equal to 0? Well, if we set this equal to 0, we're going to get that x is equal to plus or minus 1. Now, you'd want to use the first derivative test to check to make sure that there's a change in sign of the first derivative. There is. So basically, I've got the answer here. These are the critical numbers. So I'm telling you, to maximize the area of this rectangle, we actually want to go to x equals 1 or -1. And x equals -1. And by the way, you can just look at this picture, but you can plug it in as well. And you can see that the y value here is, I think it's a half. So the coordinates of the vertices of the rectangle with maximum area are going to be 1, 0, 1, half, -1, 0, and -1, 1/2. And I think we're a little bit past time here, so I'm going to go ahead and stop the lesson. So hope that makes sense. You need to review those ideas on the Canvas page and do the homework on WebAssign if you're doing WebAssign. Have a good day.